In the previous lesson, we learned that atoms have a characteristic emission spectra and absorption spectra. So atoms can absorb light of certain frequencies and emit light of those same frequencies. Now we know that there are different kinds of atoms. So hydrogen has 1 proton, helium has 2, lithium has 3, and we're not showing the neutrons here. But if an atom has more than 1 proton, you're going to need neutrons to keep the nucleus of the atom together. And then we have the same number of electrons orbiting the nucleus as protons. This makes the atoms neutral. And we talked about how we can think of as the atoms have more and more protons, they're heavier elements. So the element is a substance made of one kind of atom, and we can sort of think of atoms as being lighter or heavier, depending on the number of protons they have. Now we said the electrons exist in orbitals with different energy levels, and we can think of the energy levels like floors in a hotel. The first floor can hold 2 beds, so 2 electrons can exist on the first energy level, and the next energy level can have 8. But notice carbon only has 4 electrons in that outer energy level, and so it could potentially take 4 more electrons. And this is the key to chemistry, that it's as if the atoms are trying to fill up their outer energy level with the maximum number of electrons, and this determines how many chemical bonds an atom typically makes. But we'll learn more about that in later lessons. For now, though, not only do different kinds of atoms have different numbers of protons, they also have different energy levels for the electrons to occupy. So we're not really showing that in this diagram. We're going to go back to our step analogy. So here we have the hydrogen atom on the left and the helium atom on the right. And the idea is that the electrons in the hydrogen atom, they can occupy higher steps, but the steps are arranged a little bit differently than the steps for the helium atom. So here's the helium electron, and the jump from the first energy level to the second energy level is a big step, whereas for the hydrogen, it's a smaller step. Now this is just sort of just to get the idea. The basic the concept here is that atoms have different structures of energy levels, a different staircase, you might say. And that means that there will be different energies associated with making any transition from one energy level to another energy level. So it takes different energies to bump the electrons to higher steps. In the case of hydrogen, it will take a smaller amount of energy to bump it from the ground floor to the next step. Helium, that's a big step there. It'll take more energy to bump it up to the next step. Well, likewise, when electrons on higher steps fall back down to the first step, different amounts of energy will be released from different atoms. They will emit different colors of light. Remember, the different colors of light are associated with different amounts of energy. And so here we see then the emission spectra of hydrogen. Notice again we have the red bar and the blue-green here and the violet. But look at helium. This is the characteristic pattern for helium. It has a different arrangement of steps, and so it can emit different colors of light. Likewise then, the absorption spectrum will be different. So again, the absorption spectrum is against the background of the continuous spectrum, all the colors of the rainbow, and the dark lines would be the colors of light absorbed by that atom. So hydrogen absorbs these patterns of colors, and helium absorbs these patterns of colors. Notice again that the absorption spectrum and the emission spectrum line up. The atom emits the same colors of light as it absorbs. Here we see the emission spectra for lots of different kinds of atoms. And so notice then they have different and unique patterns of light that they emit. And that's because different atoms have different arrangements of energy levels. This is really useful for astronomers. So the emission or absorption spectrum can be used to identify atoms. This means that light emitted or absorbed from an object or cloud of gas can be used to determine what atoms are present in the object or gas. So we've seen this before. We have a light source, and here we have a cloud of gas. Let's say we don't know what the gas is. But if we measure its absorption spectrum, and we can determine the patterns of these dark bars, we can then compare that to laboratory samples, and we can figure out what this cloud of gas consists of, because certain atoms absorb light of certain colors. And this allows astronomers then to determine the chemical composition of a cloud of gas simply by measuring the light that is moving through that cloud of gas. So we'll use this final slide to summarize what we learned. Here we have a light source, and we'll assume it's producing white light, all the colors of the spectrum. Now, if we just pass that white light through a prism, we will record the continuous spectrum. And we've learned about an absorption spectrum. If that light goes through a cooler cloud of gas and we pass that light through a spectrum, we'll see the continuous spectrum with these dark lines. The dark lines are the frequencies of light that have been absorbed by the cloud of gas. But as those atoms are absorbing the light, they will eventually emit that light as well. And if we just now sort of measure the light coming from the cloud of gas, not in line with the light source, but if we emit the light coming from the cloud of gas, we will see the emission spectrum. So these are the colors of light that those atoms emit as electrons jump back down from higher energy levels. And notice the emission spectrum pattern is identical to the absorption pattern. So this cloud is made up of a certain kind of atom, and we can determine its identity based on the pattern of the absorption lines or the emission lines.